All right, this is a question. Prove that integral 0 to infinity e to the minus ax into x to the power n minus 1 dx is equal to gamma n divided by a to the n. Here we need to take that where uh, a and n are positive, where a and n are positive. So this is given that it is always positive. Okay, so let us start this. I start from the LHS, that is integral 0 to infinity. This is e to the minus ax into x to the n minus 1 into dx. This is equal to, okay, before I make any further proceedings, we need to make a substitution here. So I'll write, so let the ax, whatever I see as a power, I'm going to put that as equal to t. So this means x equal to, because I need a dx now, so I'm writing this t by a. So dx should be equal to dt by a. This is my first substitution. Okay, and I note that from the given this thing, if x is varying from 0 to infinity, in this case t will also be infinity, because x is 0, t is 0, x is infinity, t is infinity. I'll write, and t varies from 0 to infinity. Okay, so this means, let us make a substitution. This is equal to, so this is equal to integral t is equal to 0 to infinity. This is e to the minus t, e to the minus t into t by a, because x is t by a, to the power n minus 1 into what? Into dt by a. All right, so this can be further extended as follows. You see that there is a to the power n minus 1 here into one more a in the denominator. So this a to the power n is the term I'm going to get. So this is equal to 1 divided by a to the n into the integral 0 to infinity, 0 to infinity. Now you see what I get is e to the minus t, e to the minus t into t to the n minus 1 into dt. So already I know the definition of a gamma function. So that means the integral can be replaced by gamma function. This is gamma of n divided by a to the n. So that is the right hand side. Okay, so that's how we can prove the theorem. All right, let's go further. Next theorem is, show that this is the one, integral 0 to infinity e to the minus ax into x to the n minus 1 cos bx into dx. This is equal to gamma n into cos n times theta whole divided by r to the n. And so there is also this question, this theorem has two parts. Okay, the second part is like this, and integral 0 to infinity e to the minus ax into x to the n minus 1 sine bx into dx is equal to the gamma of n divided by, this is r to the n into sine of n times theta. So these two needs to be proved. Okay, here we have a information given where, right, the r square is equal to a square plus b square, and theta should be equal to tan inverse of b by a. I can use this to prove the above statements. All right, so now we know that just now we proved one theorem, so we'll use this. Okay, so that is, we know that okay, we know something. Just now we proved that is integral 0 to infinity e to the minus ax into x to the n minus 1 dx is nothing but this is gamma n by a to the n. So this is what we already know. Now I'm going to use this to prove the points. Okay, so replacing the a by a plus j times b. It's a complex number. I try to replace the a by a plus j times b. This implies on both sides I'm going to make the same replacement. Okay, so that is integral 0 to infinity. This is e to the power minus, so a is there, I'm supposed to write a plus j times b, okay, into x. My first point, into x will not change, x to the power n minus 1 dx is going to be equal to the same gamma function divided by, this is a plus jb whole to the power n. Okay, so now I know that e to the power, if I can write the e to the power number, right, I can make a modification. I'll split the e to the powers now. Okay, this is equal to 0 to infinity. See, e to the power minus ax is the first term. Second term is e to the power minus jbx, second term. X to the n minus 1 dx is going to be equal to gamma n divided by the a plus jb to the power n. All right, now I have a identity. E to the power j theta can be replaced in terms of cosine and sine values. Okay, if it is positive, you have a plus sign. If it is minus, like what I have now, e to the power minus jbx, I'm going to write it as a minus sign between the cos and sine. Okay, so that means this is integral 0 to infinity. We'll keep the e to the power minus ax as it is, but e to the power minus jbx is nothing but cos b times x minus j times sine bx. All right, this is what is a substitution for e to the power, this number. Okay, and now this is going to be, this is equal to the right hand side. We will not make any modification. Right side remains as it is. So that is gamma of n, that is gamma n divided by a plus jb to the n. Okay, now the next step is simple. We try to equate the right hand side. We want to express that in the form of, say, real and imaginary. Then only I can actually do an I can actually equate. Okay, sorry, I think I missed the x to the n minus 1 and this. Sorry, let me write that now. So here you can see that I missed the, I didn't complete the integral. So let's finish that first. So this into, I have x to the n minus 1 dx. Okay, this is equal to the gamma of n whole divided by a plus jb whole to the power n. Right. Now, in order to bring it into the required format, what I try to do here is I'll make a substitution. Okay. So on the RHS, let's make the substitution. Already they have given, right? So put A is equal to R sine theta, or okay, let's go for a cos first, then we'll put the sine. Okay. So this is R cos theta. This is R cos theta, and put B is equal to R into sine theta, right? In such a way that this implies, what's the meaning of this? R square is equal to A square plus B square, obvious, and theta is equal to, this is what is given already. Okay, this is B, theta is tan inverse of B by A. Just to satisfy this, we are writing it in this case. Okay, so this means I still have the left hand side same. I'll write the left hand side first. This means it is integral 0 to infinity e to the minus ax into cos bx minus j sine bx into it's x to the power this into x to the power n minus 1 dx. All right, this was the left hand side term. This is equal to, on the right hand side, I'm going to make this substitution. So a plus ib can be written as, so we know from the basics of complex numbers, I can write the RHS as follows. This is gamma function, gamma of n numerator divided by, see, a plus ib is nothing but, I can write r, that is the magnitude of the complex number, into, so r whole power n, because there is a power n over there. Okay, anyway, right, I'll write the power later. So r into e to the power j theta whole to the power n. Why I'm writing this? Because, so I'll write in bracket, this is because a plus jb is equal to r e to the power j theta. So what is this form? This is called as the rectangular form of complex number. So this format is called as the polar format. In the sense both are equal, I can definitely write it in this way. So you see that in the previous equation we had a plus jb to the power n. Now I'm going to replace it by this term. Okay, so let's expand, keep the left hand side as it is. So this is equal to the gamma function whole divided by, this can be written as r to the power n into e to the power j n theta. So the power comes inside. Okay, j n theta. Now what I do, I try to further extend this. So this is, put the gamma function as it is, gamma divided by r to the n. I'm taking the exponential term to the numerator, e to the power j n theta in the denominator. When it goes to the numerator, we know that the power sign will change. So sign becomes negative, minus j n into theta. Okay, so that is further, this is equal to, I'm going to write it in this fashion, gamma n divided by r to the n. So e to the power j n theta is nothing but, once again, this is cos n theta minus j sine n theta. All right, so let me write what is there on the left hand side first, just to make sure that we are following the rules. So this is integral 0 to infinity, this is e to the power ax into, inside the bracket we have cos bx minus j sine bx into, this is x to the power n minus 1 dx. So we have two terms, right, to compare. So now I need to compare the real and imaginary parts on both the sides. Okay, how do you do that? You can do it in the following fashion. Let me write the terms expanded now. So that is, first integral is like this. This is integral 0 to infinity e to the ax cos bx, right? I'll multiply the x to the n minus 1 inside. Okay, this is into x to the n minus 1 dx is my first term. Then I take the minus j times integral 0 to infinity. I'm writing the left side only. Okay, that is e to the ax, cos is over, so sine bx into x to the n minus 1 dx. This is the left hand side expanded. Whatever was the bracket, we opened that. So this should be equal to, now I multiply the gamma to the n into r to the n sine theta and cos theta. That I'm going to multiply and write two terms now. So this is equal to, on the right hand side, gamma n by r to the n into cos n theta, first term. Second term, minus j, okay, this is gamma function, gamma of n into r to the n, this is sine n theta. So now you see that when you equate the real and imaginary terms, this is the real term on the left hand side, this is the real term on the left hand side. So they have to be equal. And, right, I understand the same thing on the right side. That is, this is the imaginary term on the right side. Leave the minus j, because both sides I have minus j, I can neglect this. So when you remove that part, whatever remains without minus j is the imaginary term on both the sides. So let us equate them, and once we equate them, we get our answer. So the final step here is to write equating the real and imaginary terms on both sides of the equations. When you do that, so now I'm equating the terms highlighted using yellow color. So that implies, this is the first part, that is integral 0 to infinity e to the ax into x to the n minus 1 cos bx dx is equal to the gamma function by r to the n into r to the n into cos n theta. Okay, also when you equate the imaginary term, integral 0 to infinity e to the ax x to the n minus 1 sine bx dx is equal to gamma n by r to the n, this is sine n theta. Hence we got the proof. So this is the question. Show that e to the 0 to infinity e to the minus ax cos e to the minus ax x to the power n minus 1 cos bx dx. So this is the term. We should be able to equate that to the gamma n cos n theta by r to the n. And another part is the same function but with the sign. So e to the minus ax x to the n minus 1 sine bx dx should be equal to gamma function gamma n r to the n by r to the n sine n theta. Okay, so they have given a detail that you can use r square is equal to a square plus b square. Theta can be equated to tan inverse of b by a. That's the given data. So what we do here, we we know something already, right? What we know here is this: e to the 0 to infinity e to the minus ax x to the n minus 1 dx. That part we already know that It's a theorem, it's a standard theorem saying that you can equate that to the gamma n by a to the n, right? So in this, we replace the a by a complex number, say a plus jb. Okay, if that is what we substitute on both the sides where I see a in the previous theorem, I am supposed to replace that with this number. You can see here, this is a plus jb once here, and once again I am replacing over here. So two times I substitute, because every a I am going to replace it as a plus jb to the power that number. Okay, now this means, right, once I replace that I get this. So you see that e to the power, there are two terms in this. One is minus ax, another one is minus jbx. So we'll split that. You can see that I split in this fashion. Right hand side still remains same. So the next step, I know that e to the power minus jbx, right, can be replaced in this format. It is cos theta minus j sine theta. E to the power minus j theta is this. Okay, I know that. I will substitute. Right hand side is still same. Now I'll make the modification on the right hand side. Keeping the left hand side same, I touch the RHS now. So in the RHS, we will make a substitution. R equal to a cos theta, b equal to r sine theta, so that you can convert that into the polar format of the complex number. So anyway, we are not using them in the equation, okay, but this is what is given, indicating that you have to use this so that you convert. So conversion happens automatically here, you don't have to show anything. We should know that, okay, a plus jb can be replaced by r into e to the power j theta, provided these conditions, whatever mentioned over there, right, those conditions are met. Okay, so let's make a substitution now. So left hand side still remains same. I'm going to modify the RHS. So simply replace the denominator a plus jb by r into e to the power j theta. Okay, once that happens, right? So we have two things coming up now. So the denominator can be expanded further. So r e to the j theta whole power n can be written like this. I can put the power, I can bring in the power to get this. So r power n e to the power j n theta will come into picture. So out of which I keep the gamma function and the denominator r to the n as it is. What I do, I'll take the denominator e to the j n theta to the numerator. So this becomes e to the power minus j n theta. Alright, so next step, now I bring the left hand side as well. So when you bring the left hand side, this was the original content on the left hand side, and right now I got this as the RHS, because here I'm going to replace the e to the power exponential e to the power minus j n theta by cos and sine, cos n theta minus j sine n theta. Okay, yes, once you get that, now you can see that the left hand side can be expanded because there is a bracket. I open the bracket. Right hand side also has a bracket. I will open this. So when you open this, you are going to get this whole equation. So I see that my LHS has two terms, one real, one imaginary. So first term is the real term on the left hand side. Second term is the imaginary term on the left hand side. Similarly, right hand side also has two terms. This is the real term and this is the imaginary term. So in the sense, what the equation which we have here, right, left hand side as well as right hand side, there are complex terms. Now from the basics of complex numbers, we know that two complex numbers are equal only if their real and imaginary parts can be equated separately. So using that, right now I understand that this is a complex number on the left hand side as well as the right hand side. So to equate them, if they are equal, their real terms should be equal and imaginary terms also should be equal. Correct? So that's why the next line you can see that I have written equating the real and imaginary terms of both sides. Equate reals, whatever is in the yellow side, right? You get this. This is the first part. The same thing was asked over there. Okay, to prove. Second, when you equate the imaginary terms, you are going to get this. Okay, so this is nothing but the second part of the equation. Hence, proof. Okay, now let's go ahead. There are Okay, we have few more theorems to come up. Now let's go to this one. The next theorem to prove is this. So show that integral, this is 0 to infinity x to the n minus 1 cos ax dx. This is equal to gamma n by a to the n into cos of n pi by 2. And there is a second half to this question, that is, whenever I have a sine I can have a cos as well. Okay, so here we have a cos given first, so I'll write a sine term next. So this is 0 to infinity x to the n minus 1. This is sine ax dx will be equal to gamma n by a to the n into sine of, this is n pi by 2. Okay, all right, so what we do now, we'll start with the following equation. So to start with, let we consider an I as a term to denote an integral. So 0 to infinity, we start from this. This is x to the n minus 1 into e to the power minus I times ax dx. I'm going to start with this. So e to the iax or jax, let me write a j here because j is more suitable to represent the complex number, e to the power j theta, right? So where this, I'll write, where the e to the power minus jax is nothing but, what is that? This is cos ax minus j sine ax. Okay, I know this, right? I'm going to use this here. All right, so that's my integral, so I denote it as I, but I'll make a substitution. So that means I'm going to put say j times ax is equal to t. So this implies I need the x as well. Okay, so what is x? X is equal to t by, this is j times a. So this implies what? What is dx? Dx is equal to dt divided by j times a. So what is the limit of t? It's the same as x. T is going to vary from 0 to infinity. Right. Now I'm going to apply this to the given equation, that is I. Therefore, I is equal to integral 0 to infinity. Now this limit is for t, so previous limit was for x, so I'll specify once now. This is equal to, so x is nothing but t by j times a. This raised to the power n minus 1 into e to the power minus, right? You can see that the jax itself is the t. Okay, so I'm going to write this as e to the power minus t into what? Into dx, but dx is dt divided by j times a. Okay, so let's simplify this further in the next step. So this is equal to, right, I can see that I have I in the sense j, sorry, my mistake, it's a complex number denoted by j that has n minus 1 first and one more power after coming up here. So I'll just highlight this now for you. So you see that this j to the power, this is the j raised to the power n minus 1, and another j here. Okay, so that means it is j to the power n in the denominator. Okay, so this is equal to 1 divided by, I got my first term, this is j to the power n. Similarly, I have a as well. With the j, I have a to the n minus 1 and a to the power 1 in the denominator. That gives me a to the n. These are constants. I can take them out of the integral. So remaining terms I'll write 0 to infinity. This is for t. So you see, when j and a has gone out, what I have? I have e to the power minus t into t to the power n minus 1 dt. Alright, so what is this now? This means this is equal to the numerator can be, the integral is gamma n j to the n a to the n. Alright, we came up till here. So what is there on the left hand side? I can actually equate that now. This is nothing but we started with this value, integral, that is 0 to infinity, integral 0 to infinity. We started with this, that is x to the power n minus 1 into e to the power minus j ax into dx. So I'll move this equal to the right side. Sorry, I will erase this. So I need a space for writing the dx. E to the minus jax dx. This is equal to this. This is what we prove now. But this is not the proof of what they have asked. We use this to prove the required equation. Okay. Now, so what I do, I'll try to make a substitution on the right hand side. Okay. So in this case, let we put j is equal to r times cos theta, because it's a complex number, r times cos theta plus the j into sin theta. This is what I want, right? So which means if you expand this, this is r cos theta plus r into j sin theta, jr sin theta. This is nothing but j. Now this means I can actually, comparing the left hand side and right hand side, I understand that r is equal to 0 because there is no term on the, this is something like 0 plus j, right? R should be equal to, not r equal to 0, r cos theta equal to 0, sorry, my mistake. So left hand side, the 0 has to be equated. I'll color what I'm equating. So you can see that the 0 I'm going to equate with r cos theta, and the next term, that is j, which is here. Okay, I'm going to equate this j with jr sin theta. They have to be equal. Only in that condition I can say that yes, whatever we are doing is right. Okay, so r should be equal, it's not r equal to, sorry, it's r cos theta equal to, yeah, so this is r into cos theta should be equal to 0, and the r into sin theta should be equal to 1. In the sense, j is equal to jr sin theta, j cancels, so what remains is this. Okay, when I have this, right, let's try to make a division. Okay, make a division in the sense, whenever we have this condition, r cos theta is 0 and r sin theta is equal to 1, correct? I can squaring and add both terms, right? So this implies square both sides, r square cos square theta plus r square sin square theta. Left hand sides I am equating equal to right hand side, 0 square plus 1 square, that is equal to 1. But what happens now, if you take r square common, the cos square theta plus sin square theta is equal to 1. Means what? So I know that this term is 1, so I don't have to take care of this. This implies r square equal to 1. Okay, that's my first term. This implies what? Right? R should be equal to 1. That's a value I'm going to get. Anyway, I'm not using this, so I don't want to calculate. And I divide those two equations. R cos theta equal to 0 and R sin theta equal to 0. Both the terms what I have, right? I'm going to divide one another. So now I'm going to divide. So when I divide, I'm going to get this. Okay, let me divide the term. And so r sin theta by r cos theta is equal to, you know that r sin theta is 1, r cos theta is 0. That's already given. This means r cancels. Sin by cos is what? Sin by cos is tan. Okay, so this is tan theta is equal to infinity. So theta is equal to pi by 2. Tan inverse of infinity, when you do that, you get theta is equal to pi by 2. Okay, so now let's try to write this further. Therefore, let us substitute. This implies I can write r equal to 1 here and theta equal to this. So already we assumed that j is equal to, right? If you remember, we wrote r times cos theta plus j times r into sin theta. Now we know the values, correct? So I can write this as r is equal to 1 cos pi by 2 plus j, r is 1 into sin pi by 2. Okay, I got this. Now this is nothing but this is equal to, anyway, this is the rectangular format. I can convert this into e to the power j pi by 2. Okay, that is the j. J can be written as e to the power j pi by 2. Therefore, you see the RHS what we got earlier. I go back and just to show this, this is what is my equation. Right? What I do, I bring the same thing now. I take that term and I copy and I paste so that I can continue from where I stopped now. Okay, so for that reason, I'll slightly go back and I copy the term and I write. Okay, so okay, let's copy this. I'll paste this. So we already have written till here. Now we are continuing from there. In this, I use the above equation. You can see that the j has been proved as e to the power j pi by 2. Okay, so this is equal to the gamma n whole divided by, see, j is nothing but e to the power j. There is a n coming up. What is that n? N is nothing but n pi by 2. J power n, j is equal to e to the power j pi by 2. So which is nothing, I will multiply by n into a to the power n. So let's go back. This is equal to, very similar to the previous case. If you remember, this is gamma n by a to the n into e to the minus j n pi by 2. So this is equal to gamma n by a to the n. Expand e to the power j theta. E to the power j theta is nothing but, that is, sorry, this was n, this is minus j. So I have cos n pi by 2 minus j times sine n pi by 2. So what is there on the left hand side? Let us expand. So here I'll write as it is. So this is simply integral 0 to infinity e to the power, not e to the power, I think we have x to the n minus 1 e to the minus j ax dx. This is there. Now I can see that, right, this term can be further expanded. On the left hand side, whatever I have, I can expand this. So when you expand this, this becomes integral 0 to infinity x to the n minus 1. So the e to the power can be written as cos of ax this is cos ax minus j sin ax into dx is equal to, on the right hand side also I have the same term, okay, that is gamma n whole divided by a to the n into the cos n pi by 2 minus j sin of n pi by 2. Okay, now let us expand the terms because we can see two brackets, right? Both brackets let's expand. So the first bracket, that is on the left hand side, 0 to infinity, right? X to the n minus 1, this is cos ax into dx. Second term minus j, then I'll write the integral 0 to infinity, this is x to the n minus 1 into sin ax dx. All right, this is what is the expansion of the left hand side. I equate this is equal to gamma n by a to the n, this is cos of n pi by 2, my first term, minus j times, once again, gamma function by a to the n into, this is sine of n pi by 2. So now I can see that I can still compare the real terms on both sides. This is the real term on both sides, and when I want to compare the imaginary terms on both sides, this is what I am going to compare. Okay, I'll compare this. So in order to get the final answer, I need to write that one statement, that is comparing the real and imaginary terms on both sides. What do I get? So the first term is 0 to infinity x to the n minus 1 into cos ax dx is equal to the gamma n by a to the n into cos of n pi by 2. This was the first part of the question which they had asked, and we'll equate the imaginary part, minus infinity to infinity, sorry, 0 to infinity x to the n minus 1 sin ax dx is equal to the gamma function by a to the n into, this is sine of n times pi by 2. All right, so that's the proof. All right, now then let's go to another question here. So that is, show that this is 2 times a to the 2 times a to the n integral 0 to infinity x to the power 2n minus 1 into e to the power minus of ax square dx is equal to gamma function. This is a gamma function. All right, so let's start with the LHS. In the left hand side, that means I'm going to start with uh, 2 times a to the n integral 0 to infinity. This is x to the power 2n minus 1 e to the power minus ax square dx. This is my LHS. Okay, what I'm going to do, definitely when we start with the integration, we need to make a substitution. Okay, so first, but always remember, in every problem of this kind, whatever is the e to the power term you can see there, right? That itself you need to make a substitution. That's the trick here. Okay, just understand that it will be easy for you. So in the sense, substitute something for that. What I'm going to substitute, I'll put t is equal to ax square. The minus you can keep as it is. Look at the previous problems also. We have done the same thing. Okay, so e to the power something is there, excluding the negative sign, substitute. Okay, so in this case, t equal to ax square, right? Under such condition, if you want to, there is a dx over there, I need to make a substitution. So let's differentiate. So dt is equal to 2ax dx. All right, so this implies dx has to be, if you want to write a dx replacement, it should be dt divided by 2ax. Okay, I don't want x present in this case. I want to make a substitution. So here you can see that what is x square is equal to t by a, so x is equal to root of t by a. So I'm going to make that substitution here. So this is equal to dt divided by 2a into x is nothing but root of t by a. So this a cancels with this as a root, so I have the term dt divided by 2 times root of at. Okay, I got this. Now put everything back onto the equation. All right, so this is equal to, there is a 2 times a to the n, which is as it is. I'll keep this integral 0 to infinity, no change in the limit of t. Okay, now what is x? X is nothing but root of t by a. So x to the power, I'm going to write it as t by a to the power, t by a to the power 2n minus 1. So 2n minus 1 into e to the power minus ax square was replaced as t. Okay, into the dt divided by 2 times root of at. All right, okay, let's proceed. So this is equal to, right, this 2 I'm going to cancel with this 2. You see, we'll try to simplify as quickly as possible. So this is a to the n integral 0 to infinity. See, the root of t by a has actually two powers. One is 2n and one is minus 1. Okay, what I'm going to do, I'm going to write it in this way. This is equal to under root of the t by a, I'm going to raise it to the power 2n first, and the second term is minus 1 is the power. What is minus 1? You flip the term. Okay, anyway, I'll write this once. So this is root of t by a to the power minus 1. You can see that the 2n minus 1 has been split. So I'll highlight with color so that when you trace, you will get the meaning of 2n minus 1 has been split, 2n and minus 1. All right, so that's the term. Into, I have the e to the power minus t as it is. So that is e to the minus t as it is, into dt divided by root of at. This is what I have. Okay, in the next step, this is equal to a to the n as it is, integral This is 0 to infinity. First term I'll keep as it is. This is root of t by a whole raised to the power 2n. But the second term has a negative power. Negative power in the sense you are actually flipping this out. So when you flip this up, this is a by t power 1 into e to the minus t into dt by, I'll split this root a into root t. Why I split? Because you see now I can cancel the root a. Root a and this numerator root a will cancel. Denominator has a root t and root t. Root t is t. Alright? Okay, so let's write that. This is equal to, now a to the n as it is. Okay, integral 0 to infinity. You see one thing in the first term, there is a square root and there is a square. So square root and square will cancel. I can simply write this is t by a to the power n. So the 2 and root will cancel in the first term. And in the second term, you can see that there is t in the denominator and one more t in the denominator. Both has a power. Okay, both have what power? Both have the power root. So into 1 by t. Okay, 1 by root t into 1 by root t is 1 by t into e to the minus t dt. Okay, now I can see that this means this is equal to a to the n integral 0 to infinity. This is t to the power n over there and one more t in the denominator gives me minus 1. T to the n minus 1 by a to the n into e to the minus t dt. So a to the n will cancel. So in the last step, I'm going to rewrite in the required format. This is integral 0 to infinity e to the minus t into t to the n minus 1 dt. This is nothing but the gamma function, gamma of n. So that is the final answer of whatever that have been asked.